All right, everybody. Let me get slides pulled up. All right, so we're just about done with equilibrium for now. If you wind up going into a field and you have to take real Gen Chem, this is intro to Gen Chem. Real Gen Chem is a whole year-long class, so 3 quarters at the college. If it's a semester school, it's 2 semesters. And you spend like a third of that class working on equilibrium. Because it turns out equilibrium has lots of applications and lots of really specific reactions have their own sort of version of equilibrium constants, so that you don't have to write out the entire equation every time for certain reactions. So one of those, the most common of those is acids. Weak acids and weak bases have their own standard, what we call dissociation reactions. So what that means is if you put acetic acid in water, the acid acts as an acid, water acts as a base. So try writing out that entire reaction. And then the equilibrium constant for that reaction is given. K equals 1.8 times 10 to the minus 5. And so if every weak acid has the same dissociation in water, a lot of times we don't even bother saying dissociation in water. We'll just say the Ka for acetic acid is 1.8 times 10 to the minus 5. Ka, written like this, means dissociation of that reaction in water, or the equilibrium constant for that weak acid in water. So with that in mind, start by writing out the reaction. And our end goal here is to figure out what is the pH of the solution where your starting concentration is 0.8 molar. Your initial concentration of the acetic acid is given at the top. What's the pH? So start by writing out the reaction and remembering what your definition of pH is. Take a couple seconds, talk to the people around you, see if you can figure out how we're going to get there. How are we going to get to equilibrium? Except it's not a strong acid. If it was a strong acid, we'd be able to do that. It's a weak acid, which means it's equilibrium, not stoichiometry. And when we do a equilibrium problem, think in terms of an ice table. So initially, does our initial concentration of water matter? Why not? Because it's water. Is liquid. What's the third rule of equilibrium? Solids and liquids don't count. Do we have a starting concentration of H3O plus? technically, but within sig figs, we can call it 0. Right, because if we started with neutral water, then technically there's 1 times 10 to the minus 7 moles per liter, because neutral water has some amount of hydronium in it. But it's so small, we could basically just say it's 0. And same for acetate. All right, what's our change row going to be? Minus X. It's water matter. For products, we're making them. So we're gaining X and X. So at equilibrium, we're going to have 0.8572 minus X, X, and X. So now how do we solve for X?
Get it on one side.
Get it all on one side. It's always best approach when you're solving for X is to get X by itself, right? More specifically though, what's the first 2 rules of equilibrium? So we know we have a value for K, and we know that the K is equal to products over reactants. We can plug something in for each of these variables now, right? X, 0.85 minus X, and 1.8 times 10 to the minus 5. Made my ice table too big. Now I don't have room to do anything else. Is everybody okay if I erase the ice table? Does everybody see where the ice table came from, what it means? I guess I won't do that yet. We'll go up here. 1.8 10 to the minus 5 equals X times X over 0.8572 minus X. We need to square anything?
Yeah.
Everything's got a coefficient of 1 here, right? So we don't have anything weird going on with the coefficients. So we can just solve for X now. So we do get an X squared once we simplify that. Now would be a good time to plug it into a calculator, or since X is pretty small, or sorry, since K is pretty small, we can do the assume X is 0. If X is really small, our next math step can be assume X is close to 0. If X is close to 0, we're still going to leave these X's alone, or else we won't have anything to solve for. But that X, we can basically just say, well, our final concentration of the acetic acid is going to be really close to our initial concentration. So we can say 1.8 10 to the minus 5 equals X times X over 0.8572. Now we can solve that. Pull a calculator out. that what I heard? We can carry an extra sig fig for right now. Sorry, 296. We'll just call that 3. So square root that, we're gonna get something times 10 to the minus 3. Seems reasonable. X is a small value. We expected X to be small. How many sig figs do we get to keep now?
Yeah.
Just the 2. What's the last step when we make this assumption? Well, not the last step, but the last step in solving for X. We could plug it back in to double check to see if our answer is close. Basically, the way we show that this assumption is valid is the X that we solved for less than 5% of what we started with. So it's going to be close on this one, right? So is X less than 0.05 times 0.8572? It should be, but barely. Unless I slipped a decimal place. Might be, no, that's 0.5%. Yeah, so it's well under, right? So basically, that's just showing your work, showing that this was a good assumption. And again, I'm not going to give you one of these on the test where the assumption's not valid, but you still have to show me that you checked it. All right, and on a homework or even a quiz question, I might give you one of these where you can't make this assumption. If K is bigger, then actually X winds up being a significant chunk of what you started with. If X is more than 5% of what you started with, you have to use a solver or solve it by hand. This case, we wind up with something that you could plug into the quadratic equation and get the real answer, right? Because we just have X squared is our highest power of X. But who wants to do the quadratic equation by hand, especially with scientific notation involved? Right? That's going to get to be a big pain, distributing that, solving, making X equals or making everything equal to 0. So if you can't make this assumption, I would recommend going to a solver. But that's just me. You do you. And pick your solver of choice. I don't know. There's Wolfram Alpha is obviously the one that I go to all the time, but there's lots of options. If you have a solver built into your calculator, you can, if you know how to use that, you can do that on the test too. Instead of making this assumption, you can use the solver on your calculator. I don't know how to use a solver on my calculator. So if I don't have access to a web browser in Wolfram Alpha, then I'm out of luck. So you make your decisions there, figure out what works for you. But you still have to say, I use the solver. If you're not going to show me all the work of getting to X, it's okay to write, I use the solver, but you have to tell me, or you're going to get marked down some points for just magically getting to a number, even if it is the right number. Okay. For this class, I use the solver is a valid math set. Are we done with this problem yet? Almost. What were we actually trying to solve for? pH. So based on what's on the board, how do we get to pH? We solved for X. X was our equilibrium concentration of hydronium, right? So if we know what X is, we know we can get to pH. So our final answer is going to be pH equals negative log of 3.9 times 10 to the minus 3. So something between 2 and 3. And how many sig figs do we keep for pH? Always the 100th place. All right, so like I mentioned before, there's a lot of different specific applications of equilibrium. There's a lot of different equilibrium constants that have like a standard form. So Ka is your standard. If you say that Ka for acetic acid is 1.8 times 10 to the minus 5, you don't need to write this whole reaction because Ka always means for a weak acid reacting with water. So what do you suppose Kb is? Anything in there have a B in it? We do like to try to stick to letters that match it. Yeah, for a weak base reacting with water. If you put a weak base reacting with water, water acts as the acid. So there's a lot of examples of weak bases, but we could use ammonia. If we put ammonia with water, we're not going to make hydronium. What are we going to get for our products? If water acts as the acid and ammonia acts as the base, what do we make? Water acts as an acid. What does acts as an acid mean? Donates a hydrogen. So what do we get from water when it donates a hydrogen? Hydroxide. And then what does the ammonia turn into? Ammonium, NH4 plus. So looks really actually pretty similar to our weak acid reacting with water, except instead of making hydronium, we make hydroxide. But there's a whole class of reactions where this happens, and so we would just say Kb for the reaction. Kb for ammonia, I happen to have that one memorized mostly because it's the exact same as Ka for acetic acid. 1.8 times 10 to the minus 5. Well, same within sig figs anyway. So a lot of times you'll just see Ka values or Kb values. That just is a shorthand so that you don't need to write this out every time. The last one that I'm going to talk about before we leave equilibrium for a bit is ionic compounds dissolving in water. You have ionic solids dissolving in water. What do they turn into? Let's say I had silver chloride as a solid, not very soluble in water. In fact, on our solubility table, it's listed as insoluble. But it actually will dissolve in water a little bit. What's it going to turn into when it does? What happens to an ionic compound when it dissolves in water? Yeah, they split up into their ions, right? So we get silver ions and chloride ions. That's going to have an equilibrium constant associated with that too, right? So every ionic, so we talked a little bit about solubility of ionic compounds and how it's like a set number. But really, the more accurate way to think about ionic compounds dissolving in water is an equilibrium process. this type of reaction has KSP. It's called KSP. SP stands for solubility product. Because what do we get as our equilibrium constant for this? What's the first rule of equilibrium? Products over reactants. And what's the third rule of equilibrium? Solids and liquids don't count. So what is KSP equal? When I say they don't count, I mean they count as 1, not 0. So it just looks like the product of the ion concentration. This actually winds up being really helpful in water chemistry and water treatment because silver is not actually a really good thing to have in your water. I know that there's like a fringe health trend for a while, drinking colloidal silver. Anybody heard of that?
What is it?
It's good because it's garbage. Colloidal silver. It's just pseudoscience where they use scientific words to mean things they're not meant to mean, so that they can sell you product. Basically, it's like a supplement that you're supposed to drink that makes you healthier, but it actually just turns your skin funny colors, and gives you heavy metal poisoning because silver is a heavy metal. I believe, if I'm not mixing this up, there's copper does one thing. I think that silver turns your skin like a bluish, almost like a bluish black. It's like pretty dark color. And not in a healthy way. Heavy metals tend to accumulate in the brain and cause problems with cognition, which is like the joke, not the joke, the insult on the playground when I was growing up was, did you eat paint chips as a child? Because paint chips used to have lead in them. If you had lead in your diet for a significant portion of your life, you had developmental problems with your brain. Silver will do the same thing. You just give yourself brain damage and funny looking skin if you drink colloidal silver. So don't do that. Why this is useful though, is if we have a water source that has small amounts of silver in it, if we want to make it so less silver dissolves in your water, we can actually just increase the concentration of chloride in that. If you increase the concentration of chloride, your concentration of silver is going to drop. And so we do the same thing with lead as well. This is one of the ways we remove lead from drinking water is we just add chloride to it, because lead chloride also makes a solid. Lead chloride, let's see, it's lead 4. So PbCl4 is going to have a similar solubility product, except it's not going to be 1-to-1. We're going to get this, right? The solubility product for lead 4 chloride is going to look like concentration of lead concentration of chloride to the 4th power. So adding a little bit of chloride to your drinking water winds up removing a ton of lead. And KSP for both of these, I think KSP for silver chloride is like 10 to the minus 10. And KSP here, I want to say it's like 10 to the minus 14. So adding a little bit of chloride, and by just adding a little bit of salt or magnesium chloride to your water, will actually remove a lot of heavy metals that can cause problems. Mercury works the same way. So this is one of the ways that they chemically treat water to make it safe to drink if it's coming from a well that has some of these heavy metals in it. All right. There are other versions of equilibrium as well. Just for the main thing, I want you to remember that capital K just means equilibrium. It's always going to come down to the first 3 rules of equilibrium. Even if you don't remember specifically what KSP is, just know that it's an equilibrium constant. The whole paint chips thing actually was a kind of a big deal because lead actually has a sweet taste to it. So in addition, Roman times, they lined the aqueducts that brought water to Rome with lead because it was a soft metal. You can basically just take a sheet of lead and push it into the groove in an aqueduct and make, a trough that would carry water pretty well, something pretty close to watertight. And actually to the point where I want to say it was the Romans actually used lead as an artificial sweetener. You could actually sprinkle lead on your food and it tastes a little bit sweeter. You just also are giving yourself a little bit of brain damage along the way, but they didn't know that at the time. All right. Let's talk about gases. So I promised after we were done talking about equilibrium, we'd start talking about gases and pressures. So let's talk a little bit about that. What is gas pressure? What is pressure, period? It's related to, that's how we used it in equilibrium. But just like in general, if you blow up a balloon, why does it stay inflated? Why does it hold its shape instead of just collapsing back down to where it is? Because the gas pressure pushing outward on it. So what is the gas pressure then? Physically, what is it? Space that the gas makes close, except space that the gas takes up, that's not, that we actually have a word for that already, right? What do we call an enclosed area in 3 dimensions? Is just volume. So volume plays an important role in gases. The size of that balloon is going to be important in describing the gas. Really, the gas pressure is basically the force of the gas molecules bouncing off of the inside of a container. So, and in terms of just like atmospheric pressure, we have gas molecules all around us, right? We're used to thinking about that. We breathe oxygen. We've all heard that before. But that means that gas molecules are constantly running into our bodies as well, right? What happens to your ears when you go over past the Carson? They pop because of the change. We've all heard that before too, right? What is that actually saying? What changes when we go from lake level to Carson City? How fast the atoms are moving? What is the speed of the atoms, or the energy of the atoms is tied to what? Temperature, kinetic energy of the molecules. So unless our temperature is changing, it's not the speed of the molecules. It's just how many. Yeah, so even though they're all the same, so if I took ping pong balls with a certain amount of force and threw them at you, it's a ping pong ball, it's not going to hurt by that much, right? If I threw 100 ping pong balls, each with the same amount of force, you're going to feel that differently, right? That might actually start to sting when we start doing about 100 times. And now think about a mole of ping pong balls being thrown at you. Even if it's the same amount of force on each ball, the fact that there's more collisions means that there's more energy being transferred to you. As small as a ping pong ball is, a mole of them would probably still crush you. Right? So what's changing about the gas pressure when you go from lake level to Carson City is how many gas molecules there are. Another way to think about it is gas pressure is related to how many the weight of all of the gas molecules above you, between you and space. There's a whole bunch of gas molecules, right? All those gas molecules are being pulled by gravity on top of you, right? The closer you are to space, the less gas molecules you have pushing on your body, the less pressure there is. All right, so if we talk about an enclosed volume of gas, so let's talk about a balloon, but a piston is the way we usually think about it. So we've got this, at its core, a piston is just a cylinder with a move where one of the sides is movable, right? So you can change the volume of the gas by pushing up or by pulling on the piston or pushing it down. That's going to change the volume that the gas has. Everybody visualize that? What's going to happen to the pressure if we make the volume smaller? They're going to bounce around about the same, but how much space we have changes. So go back to, I'm going to throw 100 ping pong balls at you again. Now, instead of just throwing them at your entire body, I'm going to focus right on your forehead. Every single ping pong ball is going to hit the same spot on your forehead. That's going to hurt a lot more, right? Than just like, oh, one on my shoulder, one on my other shoulder, one on my forehead. The same amount of collisions in a smaller space is going to feel different. It's not that we have more collisions or fewer collisions, or even the collisions have more energy. It's just that they're over a smaller area. Right? And so that actually gets to our actual definition of pressure. Mathematically, pressure is defined as force over an area. The same force spread over a larger area is, you're not going to notice it as much. Right.
It's like gas cylinders, it's like PSI.
PSI stands for pounds per square inch. Pounds is a force, square inch is an area. So PSI is a pressure unit. And the way that this kind of makes sense, the difference between force and pressure. So let's go back. So let's say we had a beach ball that weighs the same as a ping pong ball. And I throw that at you with the same amount of force that I was throwing the ping pong balls. Is that going to sting at all? Even if it's this, because it's the impact is spread out over a larger area, right? So now let's take that same amount of force and that same mass and let's shrink it to the size of a BB. That's going to hurt a lot more than the ping pong ball even, right? Same force, smaller area. Another good way to think about the difference here is a knife. The same amount of force, a knife or let's make it fun. A samurai sword, a katana versus a baseball bat. If you hit an apple with a baseball bat, it's gonna splatter. Is it gonna be different than if you put the same amount of force into hitting it with a samurai sword? Very different, right? Same amount of force. The only difference about a blade versus a blunt instrument is the area of contact. Right? So if we think about it more slowly, we have a tennis ball here. If I took a tennis ball and I took a kitchen knife or a samurai sword and I pressed down on the tennis ball with a samurai sword, what's going to happen? Might cut it in half. Probably we'll cut it in half. If I do the same thing with a baseball bat, it's not going to work, right? Same force, larger area. Right? So when we're talking about gases, it's all about pressure, which is force over the area. So when we take this piston, if we squeeze it down, we didn't change the force of the collisions or even how many collisions we have. All we did is we set the same collisions over a smaller area. So we can actually do this mathematically. This is actually what you are going to do in lab this week. We're going to make a cylinder we're gonna take a syringe and we're gonna close off one end of it. And we're gonna balance things on top of the plunger that have different weights. And we're gonna look at what happens to the volume of the gas. We're gonna change the pressure and measure the volume. If we doubled the volume. Okay, so the first thing we do is we press down on it. So if we take this and we cut the volume in half. We didn't change the force. We have roughly half the area though, right? So what should that do to the pressure? So if we cut the volume in half, the pressure should double. If we cut the volume in half again, pressure should double again. Can you ever get to zero volume?
No.
No, because what's going to happen to the pressure as you get closer and closer to zero volume? It's going to explode. Practical terms, it's going to explode. Basically, assuming we had a invulnerable piston that would never explode, pressure is going to actually approach infinity. On the flip side, if we took this and we pulled the piston out, we doubled the volume. What should happen? Half the pressure. What sort of function does that look like? Who's had algebra 2 recently? Not logarithmic, because logarithmic or exponential decay is going to have, that has an x-intercept, right? Or sorry, a y-intercept. Has two asymptotes, one on the x-axis and one on the y-axis, right? Close. 1 over x.
Yeah.
As you double the volume, pressure gets cut in half. Here's another fun thought experiment. Can you ever get to zero pressure? Well, we couldn't get to zero volume because the pressure went to infinity. In order to get to zero pressure, we'd have to get the volume to infinity. So even in deep space, the entire universe, if we consider the entire universe to be one volume, there's still pressure. There's actually measurable atmospheric pressure in deep space. It's really, really small, like 10 to the 9 times smaller than atmospheric pressure on Earth. It's something along the lines of 10 to the minus 9 atmospheres in deep space, but it's there, it's measurable. If you think your ears hurt when you go from Carson back to lake level, that change in pressure. Think about going from atmospheric pressure at sea level to 10 to the minus 9 atmospheres. That's not very comfortable. All right, so mathematically, the way that we describe this, you can say that pressure is proportional to 1 over volume. We can't quite say that pressure is equal to 1 over volume. It's equal to a constant times 1 over volume. And instead of writing equals a constant times 1 over volume, where the constant is going to change depending on the gas and temperature and things like that, we just use that symbol that kind of looks like a Greek alpha to say pressure is proportional to 1 over volume. Just means that if you plot pressure versus 1 over volume, you get a straight line that goes through the origin. Or another way of saying it is that pressure times volume is equal to a constant.
Why does pressure go up?
So the reason that we have less pressure on our ears at lake level compared to Carson City is because we're closer to space, right? The weight of the gas molecules above us is a lot less, right? Now, if you go underwater, you now have the pressure of the water, the weight of the water on top of you, in addition to all of the gas molecules above that. So I've It's been a long time since I took my scuba test. But I believe, is it every 12 feet or 20 feet is equal to 1 atmosphere of pressure? Every 20 feet? Well, every 12 feet you go underwater is equivalent of adding another atmosphere of pressure on top of you. So water is a lot more dense than gas is, than our atmosphere is. Like 10 to the -9, very close to 0. Because there's no gas molecules pressing on you. There's a tiny amount of gas molecules in deep space, but very, very small.
Is that where there's high altitude cooking instruction?
That is why there's high altitude cooking instructions. Because it will find out that water boils at a different temperature based on the atmospheric pressure. At a lower atmospheric pressure, water boils at a lower temperature. So even cooking pasta takes longer because we boil our water at 92 Celsius, not at 100 Celsius. So it takes a little bit longer. And when you start getting into baking, a big chunk of baking is allowing gases to be released at the right time and at the right proportion. And if we have less atmospheric pressure pushing on your cookies as they're baking, then you need less baking soda or baking powder, because you don't want to produce too much of those gas molecules. You want to match our atmospheric pressure. So really, you could do anything that uses baking soda or baking powder. You could probably just cut it by 20%, because we have 20% less atmosphere here. But the boiling water at a different temperature, there's a lot of variables going on, but that's exactly why. Deegan? Yeah. Because the guy did it at home and he didn't do a great job. I believe usually from an engineering point of view, usually things fail at seams and corners. So it could have been a weld that was bad. I don't know if we know enough specifics.
Carbon fiber, that doesn't stand up very well to.
Oh, the repeated flexing. Yeah.
just titanium.
Okay,
use
so
raw material.
use the wrong material. And a lot of times, even stuff that is built properly will still have its limits. And usually when you see it failing, it's going to be at a seam or a weld. Even like military class submarines have those limits. If you've ever seen a movie where it had a submarine going too low underwater or something like that, usually what they do in Hollywood to try and show that is they'll show like, the bolts breaking and water starts coming in where things are bolted together. That's actually not a bad representation of what it might look like. Yeah. There's not a whole lot of reason for the military to be able to go as deep as the Titanic. For the most part, they need to go deep enough they can't be detected, but they don't care about going to the bottom of Marianas Trench or anything. To do that, you have to get more specific, more specialized equipment. So it winds up being a different sort of problem than what the military is usually trying to solve. Kayla? Mm-hmm. There are limits. So the human body's really good at adapting to slowly increasing pressure, but it still does have limits. But a lot of those limits have to do with eventually you get to the point where the gas that you're breathing doesn't stay as a gas anymore. You wind up with it being liquid if you have too much nitrogen in it, and some certain other gases mixed in. So you have to actually use a different mixture of gases. And so if you're going really deep, you have to have 2 different tanks on your back that you switch over once you get to a certain depth. It's at Heliox, I think, that has some helium mixed in with the oxygen instead of nitrogen. It's safer for you to breathe at extreme pressures. It will also make you sound funny because it's helium. But you can breathe that at deeper pressures. I don't think you could go, there's a Guinness record for the deepest scuba dive. Yeah, something like that. That sounds right.
Is that where the bends come from?
The bends come from the nitrogen. So basically, nitrogen is pretty useless to our body. Our body doesn't do much with nitrogen, but if you get too much mixed in, it actually has a similar effect to alcohol in some ways, where it basically will impede how well you can think. And so that's called nitrogen narcosis, which the poetic name for it is rapture of the deep, which is actually what Rapture from the first BioShock game was named after, Rapture of the Deep. But they call it that because you start feeling giddy and euphoric and things like that. The bends happens when you go the other way. When you go from having a whole bunch of nitrogen dissolved into your bloodstream to coming up and removing that pressure, the nitrogen doesn't stay dissolved in your bloodstream then, and it bubbles out, causes bubbles in your bloodstream, which is really, really painful. And if it happens in your brain, is the equivalent of a stroke and you die. So the bends is what you get from coming back up. Nitrogen narcosis is you get if you go too deep with the nitrogen based tank. Leia and then Maddie. Everything has its limits. And you know, even something as the highest pressure that we have naturally on Earth is going to be at the bottom of the Marianas Trench. But actually, if you go under the surface of the Earth, the pressure at the core of the Earth, both the temperature and the pressure, now you've got the weight of rocks on top of you in addition to all the gas, and that gets even higher. But then even that can't compare to the pressure that you get when you go to like Jupiter, for instance. When you get down under the clouds in Jupiter, it's a gas giant, so there's just layers of clouds and clouds and clouds. But the deeper and deeper you go, the more and more pressure there is, and it gets to the point where it causes even hydrogen winds up forming into a solid under that kind of a pressure. So there's always going to be limits, and there's not one material that's right for every situation with that. Maddie? Yeah. So what you do to avoid having that happen is you basically give your body a chance to reach equilibrium as you come up. So you stop every 10 feet or so when you come up, and you hang out there for a few minutes to let your bloodstream get rid of that excess nitrogen, and then you come up a little bit more and wait for it to get to equilibrium and come up a little bit more. If you rush that, then you're going to get the bends. And it's really, even if you don't die from it, it's described as one of the most painful experiences that you can have. I had a family friend that was an underwater welder before you had like dive computers that you just kept on your wrist. And so you had to rely on the person on the radio doing the math for you to bring you up at the right rate. And he got the bends in his joints, in his elbows and shoulders, because the guy brought him up too fast. And I believe that words and or blows were exchanged, and I think that guy lost his job because he could have killed our friend. So it's a really big deal, but that's exactly why you go slow. And the deeper you go and the longer you stay down, the slower you have to go when you come back up. Isabel? Yeah, basically they regulate how much. They put you in a chamber that has extra nitrogen in it and extra pressure in it for an extended period of time to basically force some of those bubbles back into your bloodstream and let you come back. Because what'll happen is if you get those bubbles in your joints, they don't stay there. They won't reach equilibrium naturally, and it's just exceptionally painful for a very long period of time. So you have to go under more pressure again to get them to redissolve back into your bloodstream, and then bring it back slowly again. But it's a really long, painful process. I believe they call those decompression chambers. Depends on temperature, how big they are. So it's hard to say. It can be days or weeks.
So can't they just not use nitrogen in tanks?
They can avoid using nitrogen in the tanks, but you also can't breathe pure oxygen because pure oxygen also impairs your judgment. And so they have to use something else. And so when you're going really deep, they mix it with helium. And also it's a cost-effective thing too, to some extent. Nitrogen works just fine as long as you follow the rules. For some people, my wife and I always had trouble doing 2 dives in one day with a nitrogen tank because we always get headaches after the second one that way. It wasn't the bends, but it still messes with your head a little bit. Leonor? I mean, kind of. There's plenty of helium in the solar system. No, there are a lot of uses for helium. But you could make it up with other things. It just has to be something that what you're at that pressure. Helium is really good for that. Because you can't force it to become a liquid until like extreme pressures, more than what the human body can handle. So you can't use argon because argon will actually have the similar problem to nitrogen, not in terms of the bends, but in terms of it'll liquefy under high pressures. And then you're trying to breathe a liquid in through your mask. And that, while it's possible, it's also really unpleasant if you're not used to it. So helium is really kind of like the sweet spot. Most things we use helium for, there are other things we can use. But yeah, there is a helium shortage. It's not something we can really do anything about because it's non-renewable resource. When it's gone, it's gone. We have to collect it from the upper atmosphere, but even then it's slowly being blown off by cosmic radiation, by solar radiation. So it's short of making it through fusion. There's a limit to how much helium we have on Earth.
What would the no pressure be?
So that's a good question. Let's talk a little bit about phase change. Usually I get this a little bit later, but this is all we really need before lab on Thursday, is this idea, because you're actually going to make this graph. So we'll come back to this in a minute, but we can also take some time to talk about phase change. So basically, a lot of the gas laws we're going to deal with, we're kind of working under the assumption that they don't go through a phase change. Remember how I said that when we keep cutting the volume in half, and pressure keeps doubling, we get up to infinite pressure? It's not really what would happen though. Because eventually, if you put enough pressure on something, eventually it'll go through a phase change. It won't be a gas anymore. It turns out we can actually predict what that looks like under different conditions by plotting. Now, I always have to think about this graph. Pressure goes there and temperature goes there. Every substance has its own pressure temperature graph or phase diagram, where we kind of break it up into these different sections, where every section is a different phase. So for most substances, if you're at low temperature and high pressure, what phase would you expect to see? Low temperature, solid makes the most sense, right? Low temperature means molecules aren't moving around very much. High pressure means we're forcing them all together to be tight. So basically, under every substance has its own diagram that looks like this. Just the specifics about where these various points and lines are change. So if you're at low pressure and high temperature, what do we see? Gas. And what is this third section then? Liquid. So basically, every substance has its own phase diagram that looks like this. And if you change the conditions, we're used to thinking about water going through a phase changes all at a constant atmospheric pressure, right? So let's call this. Actually, waters looks a little different. So let's go. Slope of the line is a little different. So we call this 1 atmosphere of pressure. Basically, by changing the temperature, we're just moving along this horizontal line. And we can go from a solid, and if we increase the temperature, it goes to a liquid, and then if we keep increasing the temperature, it goes to a gas. If you drop the pressure, this line shifts downward. So if this is 1 atmosphere, this is not going to be the scale. Let's call this 0.8 atmospheres. That's about lake level. Now it'll actually go through the boiling point at a lower temperature. We hit this point where we go from a liquid to a gas at a lower temperature. That's why things boil at a lower temperature here. But if we keep going, it keeps shifting even further. If we go down to 0.1 atmospheres, then all of a sudden, let's say that we were right here. Let's say this is 1 atmosphere of pressure. Call that room temperature, 25 Celsius. If we drop the pressure, what happens to water? Kind of. It's going to boil, right? What do we call when something goes from a liquid to a gas? It's evaporating or boils. So basically, if you take the human body and you remove all atmospheric pressure from it, we dropped down to here. Basically, all the water in your body evaporates all at once.
That's scary.
So similar to the bends, your blood boils. You wind up with all of the water on your skin evaporating off, which causes your body to freeze. So you're simultaneously boiling and freezing to death at the same time.
That's why pop culture makes ice cubes out of.
That's why ice freezes on the outside of the skin. Also, your body's used to pressing outward with a certain amount of force, right? A certain pressure to counteract atmospheric pressure. If your body is pressing out with a constant amount of force to counteract atmospheric pressure, if you remove that, now your body's pressing outward with 14 pounds per square inch, and there's nothing pressing back against it. So you basically, it tends to come out mostly through your mouth and nose. You basically throw up your internal organs while you're boiling and freezing to death. It's, by all accounts, a pretty awful way to go.
We learned this through trial and error.
So experimentation, I don't want to use that word because it's not necessarily something we tried to. I believe that the Soviet Union has recorded data of some of the animals that they sent up into space and then removed the pressure from. And I don't want to call that science because it's just torturing animals, but we do know that it happens that way because of those events. Yes. So we have a pretty good idea of how that works, and why it works and why it's not very pleasant.
So in the phase shapes diagram, I know that some elements, their graphs are go to a point where it's neither solid, liquid, or a gas at a certain atmospheric pressure.
Yeah. So there's a couple of things about this that are really significant. That point right there is actually kind of cool because every substance has what's called a triple point. The triple point is a combination of pressure and temperature where you can get all 3 phases in equilibrium with each other at the same time. So at the triple point for water, you can have ice, liquid water, and water vapor all existing in equilibrium at the same time. So instead of, something like a half frozen bottle of water, you actually would have all three phases simultaneously. It would look really interesting because it would look like it's both boiling and freezing at the same time.
Forbidden slip.
Forbidden Slurpee. I like it. But every substance has that triple point. On the other hand, there's this line between solid and liquid goes up kind of to infinity. The exact specifics depend on the substance, what the slope is, what else happens once you get up there. But every substance also has what's called a critical point. And a critical point is basically when you get to a high enough temperature that your molecules have enough energy that they could be a gas. But there's too much pressure for it to be a gas. You're basically forcing them to be close together like a liquid, even though they have enough energy to be a gas.
You lost slide.
Oh, your computer's restarting. That's okay. We can do this on the whiteboard. So once you get up to this point, this line actually does stop. And you basically get sort of like a gradient up here between liquid and gas. Once you get to the critical point, where they call this supercritical fluid. Super just means extra. So, or beyond. So supercritical fluid is a point where it's not a liquid and it's not a gas, but it's kind of both. And there's a subset of that. It's where we call it what we call a plasma. Not really any common examples. The sun is not really a gas or a liquid. It's a supercritical fluid. It's basically everything's hot enough that it could be a gas, except that for the gravity of the sun keeps everything so tightly packed together that it doesn't move like a gas.
Just like a liquid, and it just really like it just has no viscosity at all.
Yeah, that's not a bad way of thinking about it. It has super low viscosity because the molecules all have so much energy that nothing's really holding them together like a regular liquid, but they're as dense as a regular liquid. So it's incompressible like a liquid, but is going to have the viscosity of a gas, which is say very, very little. The other interesting thing about this is that there's more than one phase of solids for most things. We just think of things as being, oh, it's just a solid. Solid's a solid, it's a solid. Except that you can have different solids made out of the same material. Like think about graphite versus diamond. Those are both solids, but they don't have the same properties or the same structure. So basically some things have other sections up here where we say the solid 2. Basically, like there are 11 forms of ice, 11 different crystal structures of ice. We have ice 1 is the form of ice we're most familiar with here, but if you get ice to high enough pressures and low enough temperatures, you get ice 2 or ice 3 forming. And we don't usually see those on Earth. Those are more, we see those astronomically. We can create them in labs by getting to really, really high pressures. But this is sort of an oversimplification in some ways. It's a decent way to understand phases, but it's not the whole story. It's going to have some different properties. I don't think it's a different color. There might be some of them though, but I don't think water in any phase is really going to absorb in the visible region, and that's what you need for it to be a different color. It might appear extra clear. It'd have a different index of refraction, so it might look different to the eye in a way that you can't quite put your finger on. Trying to think of a good example. So that's more the impurities, yeah. And it does have something to do with the crystal structures as well. Yeah, and really part of that is just how much ice there is. If you have a smaller amount of ice, it looks more like regular ice. trying to think, there's some YouTuber that my wife watches made a cocktail out of Antarctic ice on a cruise, and it just looks like regular ice. Once you get it to be like this size, it really looks just like water. Looks blue when you have a whole bunch of it, but in a glass, just looks colorless. All right. So those were good. Those were fun questions. And we didn't really lose any time on that because we covered the stuff I really wanted to cover. The last thing we're going to cover is what about temperature? What if we do the same sort of piston experiment, except we're going to measure the volume as you increase the temperature. So if we increase the temperature, why would you say it's going to expand?
Faster, they exert more force.
If they're moving faster, they're going to exert more force. So if we think about that piston, if we treat that piston like it's a frictionless piston, where it can move without having to deal with friction, then if the gas molecules all individually hit with more force, it's expanding against atmospheric pressure, and that's relatively constant, right? So we would expect, think about what happens if you leave a balloon in a car in the summer. It pops because it expands to the point where it can't hold the gas molecules anymore. Right, so we would expect. So let's do a similar thing with volume of the piston versus temperature. Let's say we started right here, call that 25 Celsius and call that 1 liter. If we double the temperature, what would we expect to happen to the volume? It gets bigger. Would it double? Why not? If we doubled the volume, the pressure got cut in half, right? If we double the temperature, the gas molecules should be moving twice as fast, so they should need twice as much space, right? You're right, it doesn't double. What if we cut this in half? We do get a straight line. Y equals mx plus b. It's not proportional though, because what happens at 0 Celsius? Water freezes. Is there anything else that's significant that happens? Is there still gas at 0 Celsius?
Still,
Not water gas, just gas in general. Yeah, you can still breathe when it gets below freezing, right? Yeah. So basically, Celsius is not the right temperature scale for using gas laws, because there's some point way over here where it would get to 0. Not 1 Kelvin, 0 Kelvin. It's about negative 273.15 degrees Celsius. Just about. It's still a measured number. If you get to negative 273.15 Celsius, that's the point where the volume would go to 0. Except for the fact that what's going to happen along the way? Everything. Good answer. So if we're sitting here at gas and we're going to drop the temperature. I mixed these up. Yeah. So if we're sitting here, if we drop the temperature down enough, it's going to turn to a solid. So we actually can't see this behavior. We can't get to a gas that's actually going to go to 0. volume because we get phase changes along the way. So even hydrogen has the lowest boiling point of anything known to man, and it boils at about 2 Kelvin. So, which would be negative 271 Celsius. So even hydrogen will still condense and turn into a liquid before it gets all the way to 0 volume. This would be, yeah, which still, if we're keeping it at a constant pressure, because we're still talking about our system where we've got that piston moving that in and out. If we have 2 variables changing at the same time, it gets a little bit more complicated, but we're ignoring that for now. So the temperature scale we're going to use when it comes to gases, we want to do everything in Kelvin, not Celsius. Because if we use Kelvin just takes Celsius and it redefines it as 0 being the coldest you can go. 0 is the point when volume would go to 0. Point of no return. They call it absolute 0 because you can't get colder than that. That's the point where all molecular motion would cease, and you can't go slower than 0. Right? So here we just basically took negative 273 Celsius and we called it 0. And what was 0 Celsius is now 273.15 Kelvin. So we just shifted everything. It's the same, 1 degree difference is the same in Kelvin and Celsius. We just shifted everything over so that our line goes through the origin, because then we don't have a y-intercept. And that makes all the math easier. We don't want to deal with a y-intercept in our equations, so we don't use Celsius. This would then, if this was 25 degrees before, right? So that would now be 298. This would be 323 in Kelvin. So if you double your temperature in Kelvin, the volume doubles. Right, so when we call Kelvin absolute temperature, because it's the temperature scale that allows for the line to go through 0. So we can say that the volume is equal to some constant times the temperature with no intercept. If we left it in Celsius, we'd have to have a plus B term on there. We don't want to do that because that makes our math trickier. All right. Last thing. So this is what's called one of our simple gas laws, although there's usually a different form that we write it in. Right. The first version, we said that pressure was proportional to 1 over volume. Then we rewrote that and said pressure times volume is equal to a constant. Another way of saying that is if we have a closed system of gas at a constant temperature, pressure times volume being equal to that constant means that if we change the volume, the pressure is going to change, but they're always going to equal the same constant. So if your pressure changes, your volume changes. So if you know your initial pressure and volume, and then you change your pressure, you can calculate your volume. Right? This is called Boyle's law. Is this P1 V1 equals P2 V2. And we can do the same thing with what we just did here with volume and temperature. With volume and temperature, we can rearrange it so that we can say V1 over T1 equals V2 over T2. And this is called Charles' law. I'm not going to test you on the names. I've just always found it funny. Does anybody watch Brooklyn Nine-Nine? I don't know that Charles Boyle, the character, was named after Charles' law and Boyle's law, but I choose to believe so. it helps me remember these two. Charles law and Boyle's law are our two first simple gas laws. Right? And if we keep pressure constant for a closed system of gas, we can change the volume and look at change in temperature, or change the temperature and look at change in volume. Right? So more practice with these. We'll actually do some examples on Wednesday, and then on Thursday, you'll actually measure Boyle's law. Perfectly timed.